In this lesson, we're looking at energy level diagrams for anions and cations, and we'll also look at electron configurations, both longhand and shorthand electron configurations. So let's begin with energy level diagrams for anions. Recall that anions are negatively charged ions. So it says that these diagrams are the same as the diagrams for atoms, except that because they're negatively charged, that means that they have gained extra electrons. So you add the extra electrons to the total number of electrons and then distribute them. So for example, if we look at sulfide, sulfide is just a sulfur atom that has gained 2 electrons to create a sulfide ion. Sulfur, if it is electrically neutral, has 16 electrons. Plus the 2 electrons, that means we will have to place 18 electrons in our energy level diagram. So again, I'm going to start at the bottom here. And I'm going to write 1s, and I'm going to draw a little line to designate the orbital. I put an upspin and a downspin, a big jump, and I move on to the second energy level. I fill that one up, and I have to fill up the p's. Remember not to violate Hund's rule, you go across and then double up. 3s. And 3p would be as follows. So if I left it like this, this is the electron configuration or the energy level diagram for sulfur. But we saw that sulfur gained 2 electrons. So the last 2 we will put right there. And as you can see now, it has a full outer shell, which provides it chemical stability. So let's count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, great. So we now have the right number of electrons for the sulfide ion. Try doing the phosphide ion on your own and see what energy level diagram you come up with. Taking a look at the energy level diagram for cations, remember that cations are positively charged ions, and they're different than anions. So you would basically fill the orbitals as you would for the neutral atom, but then you subtract the electrons, because if it's positively charged, it has lost electrons. So you subtract the electrons from the orbital with the highest principal quantum number. So you go to the orbital that has the highest principal quantum number, so that's basically your n, okay? And you take the electrons from the highest n. So we want to take the electrons from the highest n value. This procedure seems to produce the correct arrangement as seen in experimental evidence. So we find that ions, or rather atoms, when they lose their electrons, they tend to lose them from the shell with the highest principal quantum number. So what I mean by that is, let's take a look at zinc. Zinc normally has 30 electrons when it's electrically neutral. The zinc ion has a 2 positive charge, which means that it loses 2 electrons. And so we will have 28 electrons to place within the diagram. So what I'm going to do is I am going to first do my 30 electrons, and then I'm going to subtract 2 electrons from it. So let's fill 30 electrons in an energy level diagram. Starting from the bottom, 1s, big jump, 2s, 2p indented, 3s, 3p, then 4s, and then we have to go to the 3d orbital. Okay, so let's count these electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, so that means 30 electrons. That would be for zinc, but we have to subtract 2 electrons because it has lost them. And the highest principal quantum number here is 4. So I need to subtract these 2 electrons right here. So I'm just going to draw a little circle here, and you would subtract these 2 electrons. And this is the electron configuration, or the electron or energy level diagram for the zinc ion. Okay, and we have removed them because this 4 is the highest N. So that's where we remove our 2 electrons from. Okay. If we looked at gallium, gallium has 31 electrons in its electrically neutral state, but because it has a 3 positive charge, it has lost 3 electrons, and it's going to lose those from the highest principal quantum number. And so in total, we will have 28 electrons to place. Again, starting from the 1s, so I'm going to place the 31 and then decide where to subtract from. 1s over here, 2 electrons, jump, 2s, 2 electrons, 2p, three s, 3p, then 4s, back to 3d, and then 4p. Okay, so if we counted all these up, that would in fact be 31, but I need to subtract 3. So remember that we have to look for the highest principal quantum number, that's 4, and we will then subtract 1 from here and 2 from here, and that will give us the correct electron configuration or energy level diagram for the gallium ion. Looking at this right here, electron configurations. Electron configurations can also be used to identify elements. So if we were to take a look at this right here, which element has this electron configuration? Well, it's an element, so that means that it is an atom. So how will we find out which atom has this electron configuration? Well, let's count up the total number of electrons. 2, 4, 10, 12, 18, 20, 30, 35 electrons. So this has 35 electrons. And if it's an atom, that means that it has 35 protons. And what element has 35 protons? Well, that is bromine. Try pausing the video right now and see if you can do this one on your own and come up with the correct element with this electron configuration. Hopefully you came up with the element technetium, Tc, by counting up all the total number of electrons, which I believe in this case is 43. Continuing on, if we look at the shorthand configurations, the filled inner shells can be abbreviated as they are the same as the nearest noble gas. So if we do the electron configuration, the total electron configuration for chlorine, okay, that would be as follows. So it would be 1s2, 2s2, 2p6, 3s2, 3p5. This right here is the overall chlorine electron configuration. But this right here represents the electron configuration for neon. Right? So we look at the filled inner shells, because the filled inner shells are the same as the nearest noble gas. And what we mean maybe by nearest, the nearest like completed noble gas, right? So for example, even though chlorine is close to argon, we're looking at the inner shells here, and that inner shell has the electron configuration same electron configuration as neon. So we would write the chlorine shorthand electron configuration as follows. We do the inner shell for neon, so we'd write neon right there, and then we would just write 3s2, 3p5. And that saves us the trouble of writing all these filled inner shells. If we were to take a look at tin has a much longer electron configuration. And I'll write it out for you. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 5p2. In this case, we are going to identify the filled inner shell. This right here is the filled inner shell. This is the same electron configuration as krypton. So we just write, instead of writing all these numbers, we say, okay, electron configuration of krypton plus then also 5s2, 4d10, 5p2. So to summarize, we looked at the energy level diagrams for anions, remembering to add the extra electrons that it gained to show that the full outer shell. We also looked at the energy level diagrams for cations, and we remembered to subtract the number of electrons necessary to form the cation, and then we subtract them from the level with the highest principal quantum number, right? So in this case, it was from the 4s. In the case of gallium, we had to subtract it from both 4p and 4s. We can use electron configurations to determine the identity of elements. If I ask for which element has this electron configuration, you just count up the number of electrons, and that's the same as the number of protons, and therefore that should help you identify what element it is. And then we learned about shorthand electron configurations. So you just look at the filled inner shell, you find which noble gas has that filled inner shell, you write it in square brackets, and then you complete the rest of the electron configuration. Thanks for watching.